Morning. Thank you very much for getting up even on the last day of the conference. I also would like to thank the organizers for this opportunity for bringing us together. It's the first time I've been in India and it has been very interesting to see a place where I never had thought I would have the opportunity to. Also, as a shameless advertisement, our graduate director said, we have these posters, why don't you take some? So if you're interested in having an advertising poster for our math program, they're yours for the asking. Okay, so let's start properly. In some way, the more general question would be about matrix groups over commutative rings, but here I will concentrate just over to the integers. Matrix groups given by a finite number of generating matrices. What can we say about such groups? I want to do this on the computer, so I will need some finiteness condition, and I will use finite quotients as a primary tool. If we are over finite fields, then the groups are finite. There is matrix group recognition. I mentioned this in my lecture series a few days ago. And what it does is basically a divide and conquer approach. The data structure of a composition tree reduces it to simple groups, and basically what one just needs there is homomorphisms, which one can effectively work out. But here, now I want to go to the integers. Let me start with the most cheesy corporate slide I could find. Something business people like to advocate, and of course that is something mathematicians have long known for a long time. There it's called the Hasse Principle. We want to work locally, modulo a prime, and we want a global result in characteristic 0. And that is a paradigm which you all know from your undergraduate studies. It's sometimes called the Chinese remainder theorem, but since we are in India, I should credit it to Aryabhata and Brahmagupta, who basically worked that out many centuries ago. And in some way, what this talk will be about to show you how this applies to a certain class of integral matrix groups. So let's start actually looking at the case looking modulo. Working modulo some number, and let's initially, for the base case, look at working modulo a prime square. And prime powers basically work the same way, we just iterate. So if we work modulo prime square, we still have one reduction left we can do, namely we can reduce modulo a prime. And if we do so, we get a homomorphism from SL. I will have, my groups will always be in SL with determinant 1 to SL over the field with P elements. What is the kernel? It's the matrices which modulo P are the identity. So they look like this. And these matrices multiply. That's basic arithmetic, because if I have two P parts, I get a P square, which modulo P square falls away. They multiply by adding these P residues here. So the multiplication in this kernel really is an addition. If we want to use Lie language, it's the adjoint module. Okay. How can we work with such a group? What I will do on the computer? Well, first I will look at the image modulo P, and for that I will use the data structure I talked about earlier. I will calculate a composition tree for this group. I will get a homomorphism to the radical factor. I will describe the radical with what is called a polycyclic generating set. Presentation for the image gives generators for the kernel, and then I have these kernels which always essentially multiply by adding up these P residues, so I can consider the kernel as a vector space of matrices, and with vector spaces I can work easily. And if I have this step, and I can combine presentations to get always presentations for larger and larger quotients, and therefore get the next kernels. If I have multiple primes, I can look at the projections modulo the different prime powers, and the group is a subdirect product of these images. To get the data structure with a solvable radical, I look at the image modulo each prime. I look at the radical factors. I combine them for the different primes to a homomorphism into the direct product of images. I combine the polycyclic generating sets for the radicals. The polycyclic generating set is a generating set, as Heiko Dietrich talked about in his lecture. And then I extend it through the next layers. This is not something to read through in detail. Don't worry if this looks a mess. It's just to have once mentioned what the data structure is. And of course, though I map in the direct product, the group itself, the image could be a proper subdirect product, and in general, it will be a proper subdirect product. So what I get is a data structure which allows me to calculate the order, to do other calculations in a subgroup modulo of the integers modulo sum modulus m. That is implemented in a gap package which is called metgroup. Just some example here. The last time I gave the talk was on Tax Day in the US. That's why the number is 1040. I take SL3 modulo 1040. I can build that data structure, calculate the order, and find, for example, maximal subgroups, and that works out reasonably well. So that is settled. Okay, now let's come to the proper topic, arithmetic groups. So, roughly and very hand-wavily, an arithmetic group is a discrete subgroup of a Lie group defined by arithmetic properties on the matrix entries. So, there is some polynomial in the matrix entries which needs to be satisfied. And if that sounds a little bit strange, you all know an example. SL, your polynomial is the determinant. I mean, you don't want to write it out as a polynomial, but it is a polynomial in the matrix entries, or preserving a form. Yeah, there is a more formal definition, but basically for this talk, what you should think of is subgroups of SLNZ or SP2NZ of finite index. And I will actually have, in this case, that n is at least 3, because for 2 things behave a little bit different. These groups they are groups, so they're inherently interesting, but they also have applications, for example, to number theory, the theory of automorphic forms. They have applications in topology. Expander graphs are a famous and popular topic nowadays. And since we are here, probably I also should mention string theory, though please don't ask me about how they apply to string theory. There are theoretical algorithms for working with these groups. They have been published in the early 1980s by Grunewald and Segal, but these are completely infeasible in practice. What do I mean by completely infeasible? One of their basic subtasks is classify all groups of order n for a given n. And the n could be many 10,000s. So it is a finite algorithm which will terminate after finite time, but it is not something one can implement. So, what I want to look at is, so the situation, I have a subgroup of SLNZ or SPNZ given by a finite set of generators. Such a subgroup is arithmetic if it has finite index. So, there are 2 obvious questions. One is, can we determine whether the group has finite index? That's something where I will skirt a little bit around, because that is a really difficult problem. And the other thing which I will mainly talk about is, let's assume some oracle told us this group has finite index. Can we determine the index? And I will mainly, in the description, look at the case of SL, but the case for SP works similar. This is joint work with Alade Tinko from St. Andrews and Dane Flannery from Galway. There is a paper which just got accepted this week by Mathematics of Computation and hopefully will be out soon. Yeah. So let's briefly anyhow talk about the question of how could one prove finite index. I can look at SL and Z as a finitely presented group. The generators are elementary matrices. The relators, there is a theorem which gives relators, but none of them are surprising. They're the obvious relators you have among elementary matrices. I can write elements of the subgroup or the generators of the subgroup as words in these generators of SL and Z. That's basically what Gaussian elimination does. And then I can say I have a subgroup of a finitely presented group. There is a method I talked about, coset enumeration, the Todd-Coxeter method, which will terminate if the subgroup has finite index. But caveat, as I mentioned before, coset enumeration is a method. It is not an algorithm. It does not have defined runtime. If the index is infinite, the process does not terminate. So if the enumeration runs, even if it has run for a few days, you don't know, is it because the index is infinite or is it just because you were not patient enough? So, second, well, in some way related caveat, this is not just because we are not clever enough or haven't thought enough about it. This is inherent with the problem. SL and Z, if n is greater or equal than 3, contains free subgroups. So we have free groups there and we have the problem, the insolvability problems for finitely presented groups. So I will assume there is an oracle which promises finite index, or if you want, you can say we hope we are lucky. Okay, yeah, and this is impossible, as I mentioned in my lecture series, by translating it to the Halteproblem or the Entscheidungsproblem for Turing machines. This is a reduction to a logical impossibility, not just not good enough algorithm impossibility. Right, let's start with an easy example. I have a subgroup of SL3Z. This comes from a paper of Long and Reed. They define a whole family of groups given with a parameter T, 3 generators. You have these matrices, so if we put, say, -2 in for the parameter, we get single-digit entries in these matrices. These are really harmless matrices. And the subgroup has index about 3 million. Well, coset enumeration of index 3 million is not, you don't want to do it by hand, but for a computer, this is not really hard to do. But yeah, it already depends how much memory you had. But let's just change the number a little bit. Let's change the number to 7. Now we have this index. That's about 2 to the 64. So if you have a computer with a 64-bit processor and you have all the memory this processor can address, as far as I know, or at least as far as the secret services tell us, no one has a computer like this, and no one will have a computer like this for probably our lifetime, and probably longer. We could have 1 bit per coset. Coset enumeration needs far more. But if we just would store 1 bit per coset, that's this index, and that's just for 7. And if you believe that, then change 7 to 15 or so, and it grows even more. So that is completely hopeless with coset enumeration. But yeah, I got this number from a calculation, actually a calculation which just ran a few minutes. Okay, the main tool for working with these groups will be the idea of a congruence subgroup. A congruence subgroup is simply the kernel of the reduction modulo M. And the image will be the full SLN ZM. The main theorem is a theorem of Menneke from '65, which says if the subgroup has finite index, then it must contain some congruence subgroup. That is really a theorem you need to prove. Initially, when I saw it first, I thought, isn't this obvious? No, it's not obvious. There is something to prove, to be proven. because we want not just the kernel of finite integers, but this particular kernel. And the smallest L for which the congruence subgroup is contained in the group, we will call that the level of the subgroup. So, because we have the group, the subgroup, the kernel of the map, and then the congruence subgroup, we could calculate the index in the congruence image. And in the congruence image, that's a group modulo some modulus L. We know how to calculate in that group. So basically, once I know the level, I can calculate the index. So I will mainly talk about how can we get the level. What's the strategy? Well, I will look at the congruence images for increasing values of M to find the level, and I will do so by first finding the primes which divide the level. Then I will find for each prime the prime power dividing the level. And for that, I need a property which is basically based on the fact whether this index in a congruence image increases. So the basic idea is I look at the image, say, modulo 2, modulo 4, modulo 8. If the index increases, I continue. And at some point, the index doesn't increase anymore. And the main tool is a theorem which we've proven, which says, with some exceptions, once the index remains stable, if the modulus gets bigger by adding a further prime, then I don't need to look at that prime anymore. Then I have the maximal prime power I need. So, how does this work? That's basically a theorem about finite groups, about groups in the finite congruence image. So, let's look at the kernel modulo M. Suppose we have for a prime P that the index modulo M is the same as the index modulo MP. That's when I want to stop. Let's assume this assumption would be wrong. Let's assume the index later could grow again. Then, if I work modulo MP squared, the group G, modulo MP squared, the index is larger, but modulo M and modulo MP, the index is the same, then G must be a complement here. A complement to this natural kernel of the reduction modulo MP. Not a complement, a supplement. And our proof is essentially to show that such supplements do not exist. Therefore, the index has to be stable. Let me briefly state this. So we take a subgroup and we have a similar theorem for SL and SP. Let's suppose we look at the group modulo prime power. Let's look at the kernels reducing. What the theorem says is if I work modulo proper prime powers, modulo P to the A plus 1, then this kernel modulo P to the A plus 1 has no proper I think the plus 1 has to be, no, the plus. Oh, no, sorry. This is the kernel. This is not the images. Yeah. The kernel modulo P to the A plus 1 has no proper supplement already in this kernel, so it cannot have a proper supplement in the whole group. And in the case when I work just for A equals 0, there is a theorem which has been proven a couple of times. There is, the first proof we were able to found is due to Beisiegel from 77, where he basically just works with matrices in the case of SL. Then Weigel proved it in 1995, excluding some base cases with some heavy machinery, and we essentially proved the remaining base cases which were missing. So if I work modulo 2, this kernel has a supplement if and only if the dimension is small and the modulus is, the prime is small. And essentially what we do is, what the proof does is there is some general argument which leaves some small cases left, and these small cases we do explicit calculations and thereby check that indeed in all of these cases there exists a supplement. but I said we want to work for dimension at least 3. So if we have dimension at least 3, really just the prime 2, and there just for the case 4 is special. So there we need to look at 2 slightly differently or do a slightly extra work, but otherwise everything works through as we hope. So how? No, it's not, I don't think it's a semi-direct product, it's a supplement. So a supplement is you take from semi-direct product, you take the condition away that they need to intersect trivially. You just want 2 subgroups which generate, a normal subgroup and a subgroup which together generate the group, but you don't demand that they intersect trivially. So in these cases, there are supplements. I don't think they are anywhere proper complement. Yes. And I hope that agrees with what you know about the group. And this is really explicit calculations on the computer. If you want, I can show you later and I can give you what these are. Okay, so how do I calculate the index? Let's assume, and in some way I'm going backwards through the algorithm, how it works. Let's assume we know the primes which divide the index. What I'm taking is the least common multiple of 4 and the product of these primes, and I'm taking 4 here because in small, I really just need this in small dimension, but 2 was special. Let's look at whether for any prime the index increases when I increase the modulus by a factor, by this factor p, then the modulus gets larger, and I iterate this until the index becomes stable for all the primes, then the level must divide, must be a proper divisor of the m I have here. Why divisor? Because I forced the 4 here, it could really just be 2. And we also show that actually you don't need to mix primes here, you can work separately prime by prime, which makes the calculations easier, but isn't really more work. Yeah, I mentioned already, this is because we start with 4. Okay, why can we work separately prime by prime? Because once we project onto PSL and P, and we have a subgroup of PSL and Q in a different characteristic, I basically only can have trivial subdirect products which degenerate to a direct product. This is basically a theorem that PSL and P does not, with very few exceptions, does not embed into PSL and Q if P and Q are different primes. That's a theorem about these groups of Lie type. Right, so now for getting the primes, which is the most interesting bit. So let's start with a little bit of theory. If I take a subgroup of SL and Z, if there is a prime greater than 2, so that the G modulo this prime is the full SL and P, then actually the image module for almost all primes is the full SL and P. And this is a theorem due to Matthews, Wasserstein, and Weisfeiler, and again Weigel in a similar context as his complement theorem reproved parts of this. And such a group we will call Zariski dense. Okay. For this talk, this is the definition of Zariski dense. If you have colleagues who are algebraic geometers or you're an algebraic geometer yourself, you know that Zariski dense is defined differently. And basically what Matthews, Wasserstein, and Weisfeiler prove is that this agrees with the definition of Zariski dense. But as a group theorist, for me, this is the more natural property. Okay. Well, so what I should mention as a caveat, SL and Z has dense subgroups. So subgroups which modulo almost all prime project to the full SL and P, but which do not have finite index. And such subgroups are called thin subgroups. So they are in some way, the this goes back to the obstacle. I cannot have a general method because if I would feed a thin subgroup to my algorithm, it would just, and there are concrete examples of groups. Humphreys has a paper with examples of groups which have infinite index but modulo all p's project onto SLNP. So this goes back to the impossibility of really determining whether it has finite index in all cases. Okay, so how can I find this set of primes? Well, I need to look at the primes greater than 2, so that G modulo P is not the full SLNP, or if the prime is 2, I need to look at modulo 4. Otherwise, I would have these such supplements, and I've excluded that there are supplements. So I just need the primes which are interesting are basically the primes modulo which G is not the full SLNP. How can I find this out? Well, let's look at a representation for G into integral matrices, which is irreducible modulo 1 prime. That means the Z lattice spanned by the images of that representation. So I take the image matrices, which are integer matrices, and I consider them as vectors, and I look at the Z lattice spanned by these vectors. No, this is not necessarily the same n. Yes, this could be a different n. Yes. That has then full rank. That corresponds to absolute irreducible. And how can I then find primes for this lattice to have full, it has to have full rank, but now I want to know for which primes is the image not absolutely irreducible. That's just the primes which divide the discriminant of that lattice. I can calculate or approximate the lattice till I have full rank, calculate the discriminant, factor it, and I get primes. So that's how I can find primes. Now, how am I going to use this? Let's first look at the case, at a special case that I happen to know a transvection that's an element T such that the rank of T minus 1 is 1. And there is a theorem which actually says if the group is arithmetic, there must be transvections, but they're not always easy to find, but in many concrete cases, the generators easily give a transvection. Well, let's take such an element and let's take the normal closure of that element, of the subgroup generated by that element, which again I can approximate by something like a spinning algorithm. Well, if rho is reduction modulo a prime, then if T rho minus the identity is not 0, it must be a transvection. So if n rho, the image of this subgroup modulo rho, is absolutely irreducible, and if in odd dimension, if we have an absolute irreducible subgroup containing a transvection, it has to be SL. So for the case of SL, or in general for the case of SP, if we have a transvection, then we actually just use the n we have. We look at the Z lattice spanned by the elements of n. It must have full rank, otherwise our group clearly cannot be arithmetic. We approximate that lattice, calculate the discriminant, factor it, and we need to look at the primes which divide the discriminant of the lattice and those primes modulo which T minus identity becomes 0, so that's the GCD of the entries of T minus 1. Right, that's how I calculated this group beta 7. So there is a transvection in the long read paper. They say for these groups they give a product formula which gives a transvection. So this is though one can't obviously see it from the entries, that happens to be a transvection. This is calculated as a product of the generators, so it is in the group, and indeed it is a transvection, and I can calculate in very brief time, 60 milliseconds, that the two interesting primes are only 7 and 1021. And now I feed these two primes in my algorithm, which works modulo 7, 49, 7 squared, 7 cubed. Now it looks 1021 squared. And after about 5 minutes, it tells me the level is this product, 7 cubed times 1021, and that is the index. And that is because I have the transvection, this is a proven index. Okay. So, that's how I can calculate these indices if I have a transvection. Now, if I do not have a transvection, but I know from an oracle that the index is finite, then I will look also at different dimensions of representations. And what I can use there is that the representations of SL and P, and this is now specific to SL, that representations of SL and P are polynomial. They're given by polynomials on the matrix entries, and therefore they come from SL and Z. So I can construct the representations generically for all the primes. And what I will just do is I will look at these representations and look for which primes are all of these representations irreducible. So what I want is I want a set of polynomial representations of SL and Z so that for every all of these is a well-defined representation I can reduce modulo P. I want that for primes at least sufficiently large. They are absolutely irreducible, and if I have a maximal subgroup, at least one of these representations will not be absolutely irreducible when I reduce it, when I restrict it to that maximal subgroup. And such representations exist. For example, the Steinberg representation that follows from a paper of Malle and Zaleski, and it essentially follows because it is of so huge degree. It can't be, the degree is so big that on maximal subgroups, it can't be absolutely irreducible. But of course, because the degree is so big, this makes it infeasible for practical calculations. So, in small cases, and this is something from an explicit inspection of maximal subgroups up to dimension 11 in the book of Brayholt and Roney-Dougal, it turns out if I look at the action on homogeneous polynomials of degree at most 4, the anti-symmetric square of the natural representation in dimension 3, because 3.A6 can be a maximal subgroup, I need to take a 15-dimensional constituent of the symmetric squares of the polynomial action on the polynomials of degree 2, then these representations are enough. And yeah, the proof is just by going through the list of maximals and verifying, yes, they are not irreducible. So, what I do is, I can go through these representations, form random elements or pseudo-random elements of the image under this representation still in Z, the image, look at the lattice in Z till I have full rank. I must have full rank because the representation on the group eventually is absolutely irreducible for infinitely many primes. And I find the primes dividing the discriminant of the lattice. And then that might be too many because I approximate, but I can just look at what is the image modulo all of these primes. And if it happens to be not the full SL, I can discard it. So this is a made-up example just to have some things happening, and there the calculation took quite a while, so it finds the primes in this way, and I could calculate the index. Okay, in the last, and as I see, I still have full 45 minutes. Very good. So in the last, I think about 5-ish minutes, let me briefly talk about what happens if the group is thin, if it is dense but not arithmetic. It has infinite index. If we feed such a group to our algorithm, it determines what I would call, I don't know whether this term is used in general, the arithmetic closure, the smallest arithmetic overgroup. And Since we are here at a branch of the Tata Institute, I thought it would be amiss if I don't do this example, which is due to Singh and Venkatarama in a paper from 2014. They look at a class of monodromy groups in SP4Z, which are associated to Calabi-Yau threefolds. And in that class, 7 of them are arithmetic. And if you do some base change, the matrices look like this, with a parameter D and a parameter K. And the question they asked was, what are the indices of arithmetic closures? And there is a paper last year by Hoffman and van Straten, where they give an arithmetic group which contains the group. So they say here is a subgroup which is arithmetic, which contains the group, but they cannot prove that it really is the arithmetic closure. With our algorithm, well, notice this element happens to be a transvection. So we are lucky. So our tools will work. We were able to calculate these indices. So these 7 groups, Singh and Venkatarama already proved are arithmetic. The other ones are not. A was this subgroup from the previous paper. C is the closure we can calculate with our algorithm. Typically, it just takes a few seconds. This is time in seconds. And as you see, in most cases, actually, well, probably even in all cases, we get an improvement over the result which was prior known. And this is, unless I made an error in coding, this is the correct arithmetic closure in all of these cases. In these cases, it's actually the subgroup itself because it is arithmetic. Yeah. So let me finish with some open questions and things which still need to be done. What are in general good representations? Easily constructed, small degree. Can we get an analog result for SP or other classical groups with the representations if we don't have transvections? There we don't have, I think, as nice polynomial representations. However, it seems the degree gets larger, so we are aiming to use Aschbacher's theorem to look more at what are the different classes, how a subgroup can be proper. For practical performance, we will need better arithmetic for matrices modulo M, not just modulo P, because that's basically where the time is spent. And of course, in some way, the holy grail would be, can we prove, if we know the index of the arithmetic closure, can this help us to prove that a group, or hope have a method which might prove that the group is arithmetic better than coset enumeration, because the index is just so large that this would otherwise become infeasible. Yeah, and that's basically what I have. Dhanyavad, thank you very much.
Thank you, Alex, for this beautiful talk. And are there any questions or comments, discussion? Yes.
Yes. No, my conjecture is, sorry, I said the conjecture holds. The conjecture is, well, in some way it's already proven with a Steinberg representation. The conjecture would be, the conjecture is vague. There is a nice set of representations which will eliminate all the maximals. And in this case, it is a nice set, but I don't think this will go through for arbitrary n. And even in that case, if these would go through, the nice ones, things like symmetric square blow up if n goes bigger. Yeah.
Yes.
Okay, so what I'm using there is the representations of SL and P are polynomial. So I can give them by polynomials on the entries. And well, that certainly works for the representations I have here, and I think that works in general. I can give these polynomials over Z. that I can, okay. Okay, yeah, but so this will extend to some larger class of Lie-type groups, but it will not work for a random finite group. If I have a random finite matrix group, its representations are not polynomial. The irreducible representations are not polynomial. If I take some solvable group of order 192 given by some set of matrices, yes. Yeah. Yeah, so I don't have a yeah. So. No. So I have a group which is dense. So modulo almost all primes, the image is SLNP. Now I go through representation. Let's start with the net of the group of my group G, the group given in characteristic 0 by Z matrices. Well, I have certainly the natural one, the one given by itself. Okay, so I take that representation and I look at, by building the lattice, I look at modulo which primes is this representation absolutely irreducible. Okay, that eliminates some maximals. Now, that eliminates the case that the image that eliminates all the primes where the maximal subgroups, what I want to avoid is that the image of the group modulo some prime p is not the full SLNP, but lies in a maximal subgroup. So, if the representation, if I look at the lattice spanned by the matrices and find the primes modulo which this lattice does not have full rank, then I know modulo all other primes, this representation, and it's also the representation then of the image, is absolutely irreducible. Okay. That is still in dimension n. Okay. Now I build other representations from the original one of SL and Z. Yes. For example, on symmetric square and so on. I do the same trick. And I can build these, in some way, it's like a commutative diagram. I could go first modulo P and build, okay. The upshot is I can build these representations. You see. Okay, I need these to be able to say if it remains absolutely irreducible for all of these representations, then it must be SLNP. Yeah? Sure. If it was SPN, I probably could go through that corresponding list for SP and find out what the representations are. So I don't, at the moment, we haven't yet looked at it, what explicit list of representations would we need to build for SP. I don't think there is a fundamental obstacle. It's the obstacle is it actually doing the work that I can concretely do it. Yeah. I don't think there is from theory that should work. In practice, you need to work out the details, and we haven't done that yet.
Are there any other questions or comments?